Hello, this is Nathaniel Cook with Team Amit, Matt, and Kai for the CS433 mini project. We are presenting on the NVIDIA Kepler architecture, which is a GPU architecture. So an overview of what we'll be talking about today is I'll start us off with the GPU versus CPU discussion, and then Matt will follow with a deep dive into the processor core microarchitecture, and Amit will discuss this new feature called dynamic parallelism, which was introduced with the Kepler architecture. Then Kai will finish up with a discussion on memory hierarchy. So in discussing the differences between CPUs and GPUs, let's first look at their use cases. CPUs are designed to reduce the latency of a single thread, while GPUs are designed to increase the total throughput of all threads. And this is apparent in the number of cores, the clock speed, and the total threads in flight that CPUs and GPUs can handle. While CPUs will have 4 to 16 cores on a high-end server, GPUs will have orders of magnitude higher at 2,000, 3,000, potentially even 6,000 cores in a single GPU. Again, back to their use case, since GPUs are designed to increase the throughput of all threads, just having more cores available to do work enables them to increase the throughput of all the threads. But in contrast, CPUs, the cores themselves will run significantly faster, up to 4 gigahertz in clock speed, while the GPUs run much slower at 800, 900 megahertz, and potentially sometimes at a gigahertz. So again, CPUs, since they're trying to reduce the latency of a single thread, really push the clock speed up, while GPUs can afford to not have higher clock speeds and just have tons and tons of cores. And obviously, since the GPUs are trying to increase the throughput of all threads, you need to be able to handle many more threads in flight. So the Kepler architecture can handle 32 to potentially 64,000 threads in flight at any given time, while CPUs these days will only do tens of threads in flight. So significant differences there. And all of it comes back to the use cases between CPUs and GPUs. CPUs are trying to make the individual task very fast, while GPUs are massively parallel, trying to increase the throughput of all the threads, all the work that needs to be done, at the cost of maybe a little bit of latency because of slower clock speeds on the single thread itself. Okay, now let's look at the differences between the instruction sets of CPUs and GPUs. Each has its own use case, and so it has a different feature set. CPUs are used for general purpose computing. Operating systems run on the CPU, and they need all the features that the operating systems do. And so you see instruction sets like x86, ARM, MIPS, etc. that have very large feature sets so that they can run general purpose computing, compile almost any language down to them, and off you go. GPUs, on the other hand, have not been used for general purpose computing until recently and only to a limited scope. Traditionally, GPUs were used just to render graphics, obviously, as their name implies. So libraries like DirectX and OpenGL was what would run on the GPU to render nice 3D images to the screen, etc. Libraries like CUDA and OpenCL are new, and their libraries are around writing general purpose code for the GPUs. So you could take some C code and you compile it using this CUDA compiler or the OpenCL compiler, and it'll actually run the code on a GPU. Then the advantage of this is if you have a highly parallel application, then you can take advantage of the high throughput on a GPU, and you can run your application in a massively parallel mode across the GPU and get significantly faster results on a GPU than you would on a CPU. Cryptocurrency mining is a very common example these days. But that being said, the general purpose computing on GPUs is still very limited in scope. It doesn't have all the features that you would need to run a general purpose platform like an OS. Namely, they don't have interrupts and they don't have virtual memory. Now let's examine the differences on the die itself between CPUs and GPUs. Again, CPUs are about latency optimizations and GPUs about throughput optimizations. So CPUs will invest their resources on the die and things like reorder buffers, reservation stations, branch prediction, these kinds of things. All of this instruction level parallelism that will make it so that the single thread can execute as fast as possible without any blockers. This is the same use of the memory cache. So the cache is used for locality, so that the next instructions are readily available, as well as the next set of data that will be operated on. So all of the investment on the CPUs is about making sure that the single thread of execution has all the resources it needs so that it doesn't have to block on anything, so it can reduce the latency as much as possible. while the GPUs take a very different approach and invest the resources on the die instead of on the expensive branch prediction and these kinds of ILM features. They use just many cores, so shared, and then because they have many cores, they also invest in some shared memory, so that the cores can cross-communicate without having to go out to the memory on the device itself. And the memory cache on the GPUs isn't necessarily used to reduce latency, but increase overall bandwidth. So now let's look at how things are actually computed inside of a GPU framework as opposed to a CPU framework, because it's very different. So the first thing you're going to do as a coder is go download the CUDA environment. So it's a library, you go download it from them. It's for general purpose computing on the GPU. Then you're going to write your code in C, C++. And you pass it to the CUDA compiler, and it's going to break up your code into all of its parallel little bits. So if you're iterating over a for loop, it's kind of going to do like loop unrolling all for you. It's going to take each little iteration and create its own thread per little loop of your code, or whatever the parallel unit is inside of your code. And it's going to create a set of 32 threads, and each of that set of 32 threads is called a warp. And then that warp gets passed to an SMX unit. So a streaming multiprocessor is what SMX stands for. And on a given graphics card in the Kepler architecture, it can have, as few as one SMX unit up to like 15, 20 SMX units. And each SMX unit has 192 cores, and it processes one warp at a time. It can be in parallel, but basically think about it as one at a time. But I think that's very important about how a warp is executed is it's what's called single instruction multiple thread. So if the instruction on the thread is to do an add, then all 32 threads in the warp are all doing the same add, but they're all performing it on their own unique set of data for their thread. So that's how the massive throughput is achieved inside of GPUs. So as a high-level review, because Matt will go into the details on the SMX here in just a minute, but high-level review, you write your code, and the CUDA compiler breaks it out into its parallel bits, and the sets of 32 threads that all have the same instructions, called warps, but operating on their own set of data. And then each warp can be assigned to a different SMX unit to be able to process that data. And so, like I said, Matt will give us some more details here in just a minute on that.
Hello, my name is Matt Farrell, and I'll be discussing the core microarchitecture in a bit more detail in this section for Kepler, hopefully to give you a better idea of how the GPU's differences make it efficient at the specific tasks it was designed to undertake. So with that, let's get started. Starting here with a high-level view of the relatively new Kepler GK110, we can get an idea of the setup of components such as the SMX, caches, thread control units, that's the gigathread engine near the top, and the memory controllers. Here you can see the Kepler setup consists of 15 of the SMX units, each of which contains 192 cores, which gives you a total of 1,536 cores in this particular version of the Kepler architecture. I mentioned each core is a CUDA core, and CUDA is just the parallel computing platform that allows direct access into the instruction set and memory. That in turn allows the GPU to be utilized for some general purpose processing in addition to the specialized processing which it's designed for. Each SMX will contain many more ALUs than a typical CPU, but generally a much smaller cache as well. Just to touch on some of the non-SMX items before we move on to the detail of the SMX, I'll note that we can see the PCIe interface that'll give you access to the DRAM on the system as needed. Also the memory controllers provide the ability to load the programs directly into the GPU local memory. This setup was created with a focus on energy savings and provides 3 times the performance of the previous GPU architecture. This was accomplished by putting less emphasis on the mathematical computations, which improved power usage, but on the flip side of that, Kepler will suffer in benchmarks focused in that area. Some other new features, including items such as GPU Direct, will allow GPUs in one computer or those on a network directly exchange data without CPU or memory access, which provides it a distinct advantage in avoiding the overhead of such operations. I'll go into detail in a bunch of these items in a slide or two, but I just wanted to give you an overall look first. So let's move on to a more detailed view of the SMX. Here's a lower level view of the SMX, showing the layout of the 192 cores mentioned previously. Each of these has a fully pipelined integer and floating point ALUs. If you take a look at the diagram, you can see how many of the cores were allotted to general purpose, double precision, and special functions, which would include trigonometry, square root, other more complex mathematical calculations. The load store areas give you an idea on the scale on which memory can be accessed concurrently. And going back to my mentioning the lower power usage of the setup, one key difference from previous GPU architectures is the lowering of the clock speed. Each core will utilize the clock speed of the GPU as opposed to the usually faster shader clock, which requires that the setup have more units in order to achieve the same throughput as some of its higher clock speed predecessors. While they may be slower individually, it results in increased performance per watt, while at a slightly higher cost for the additional hardware to be built. Another key improvement with the Kepler architecture was the use of 255 registers per thread as opposed to 63 in some older setups, and provides a larger buffer for activities that are running and may spill over into main memory when local storage isn't available. This keeps data nearby and provides faster data access. Nathaniel also mentioned single instruction multiple thread. To run a thread hundreds or thousands of times is required, and I want to provide some more detail on that too. Since a warp consists of 32 threads and each warp is assigned a single instruction to run, the warp is used at maximum efficiency when the entire set of 32 threads can run that same instruction. So single instruction multiple thread is essentially a relative of single instruction multiple data, but does not expose the underlying width of raw multiple data instruction vectors to software like multiple data would in order to program instructions towards it. Single instruction multiple thread instead specifies the execution and branching of a single thread. This makes programming with CUDA slightly more abstract, but simpler to program tasks, and it is most effective when you're able to reduce the branching of execution of threads within a warp. A good analogy might be exposing or concealing cache line size. Knowing the line size can be managed by the code and take away some of the detailed code you may require in order to ensure it fits within the specifications. But coding specifically to that line size could be useful when you're specifically optimizing for high performance instead of a general algorithm making those decisions for you at a higher level that's hidden from you. Now I wanted to touch on some of the scheduling features of the SMX and a little bit on how it was improved in Kepler from previous architectures. First, it has a common scoreboard methodology, which it shares with its predecessor, that it used for long latency operations, determining who will take the longest and shortest times to execute. Amongst those that are eligible on the board, an attempt is made at optimal warp selection to obtain the highest performance possible. The gigathread object we saw in the original high-level diagram assigns the warps to the various SMXs. As for improvements from the previous architecture, hazard avoidance was an area that was improved by taking what was a hardware-based stage in processing and moving it to the responsibility of the compiler. This is possible since it was found that the latency of instructions was deterministic. This value can be calculated by the compiler and stored directly alongside the instruction information. This allows the replacement of a more complex hardware stage for determining the latency with a simple fetch for the instruction, which comes along with the latency data attached to it. Here we have a few more basic technical details of the Kepler setup, with 4 warp schedulers per SMX, 8 instruction dispatchers, and 128 threads to pipeline per cycle. One interesting note about Kepler was the introduction of a new type of instruction called a shuffle. It permits the sharing of data directly between warps, completely circumventing even the need to utilize local shared memory, allowing loads and stores to occur within a single operation. For applications which may require a large amount of data being shared amongst the tasks being executed, this can result in significant performance improvements. And lastly on this slide, I also wanted to note that double precision instructions were also permitted in this architecture to be scheduled alongside other instructions, whereas in some previous setups they couldn't be. Again, this would create advantages for specific types of applications that would utilize this. Lastly, I wanted to mention one other creative addition to the GPU setup that is more about the context of the GPU within the entire system or a network. It's a design which allows GPUs in a system or network to communicate without requiring any system or CPU access. This eliminated a lot of the overhead for system configuration, which may include multiple GPUs for added processing power. Not only can GPUs utilize this feature to communicate directly with one another, but via its remote direct memory access, it can allow third-party components such as NIC cards and video capture devices to access it directly. So this interface is again avoiding any potential overhead or bottlenecks that may exist in a typical system communication path through the CPU. So with that, I'll now pass you on to Amit, who's going to go into more details discussing some of the topics on dynamic parallelism with Kepler. Thanks.
Hi, my name is Amit Vikram Das, and I will be talking about dynamic parallelisms in the NVIDIA Kepler architecture. GPUs are actually extremely good at executing tasks that exhibit data parallelisms, especially tasks that can actually exploit the GPU's wide vector width SIMD architecture. Let's consider the following simple example. This is a nested loop that calls an algorithm 100 times. The inner and outer loop sizes are known at compile time or kernel launch time, so this nested loop can be easily unrolled and vectorized by the GPU. Each call to the algorithm can be carried out in parallel with different data inputs. Now let's consider a slightly different example. This example is much harder to unroll and vectorize for the GPU. The outer loop size is known at compile time, but the inner loop size is not known until runtime. The GPU itself is now unable to resolve the size of the inner loop, and therefore finds it a much harder problem to solve efficiently. So how do we solve the problem at hand? There are a couple of alternate methods, one of which is called oversubscription. In the oversubscription method, you basically define the data grid to be the outer loop size and the max of values in X. In most cases, you end up with a sparse matrix, which ends up being a waste of resources since execution is still carried out on those empty cells. This is not an efficient solution to the problem. Yet another method is called serialization. You basically vectorize the outer loop since the outer loop size is known, but then serialize the inner loop by basically giving back execution to the CPU. This ends up requiring a lot of coordination between CPU and GPU, and is not really efficient because it doesn't even use the full power of the GPU. So far, none of the alternate methods described previously have been able to solve this problem in an efficient manner. Before we actually solve this problem with dynamic parallelism, let's take a quick look at what Kepler and dynamic parallelism had to offer over its predecessor, the Fermi architecture. In the Fermi architecture, all work was launched from the CPU, and kernels would basically run until completion and return back execution to the CPU. Results would either be used for the final solution or would be analyzed by the CPU, which would then send out additional requests to the GPU for processing. With Fermi, the CPU was the only unit able to launch kernels and execution blocks. The Fermi architecture was very good at processing large parallel data structures when the scale and parameters of the problem were known at kernel launch time. But this was severely lacking when implementing many other algorithms. With the addition of Kepler and dynamic parallelism, any parent kernel, that is, a kernel that was launched by the CPU, could now launch child kernels and create new work for itself. This allowed the GPU to be no longer completely dependent on CPU for work. The GPU could now create new streams, events, and even manage dependencies needed to process additional work without the need for any host CPU interaction. This made it easier for developers to create and optimize recursive and data-dependent execution patterns, while also allowing more of the program to run on the GPU. Various other algorithms could also be implemented on the GPU, including nested loops with different amounts of concurrency built in. Now let's take a look at how we can use dynamic parallelism to solve the problem at hand. Let's create a new kernel for the outer loop. Let this outer loop kernel accept an integer array as the runtime input parameter. Inside the outer loop kernel, let's loop based on the value obtained by indexing into the data array using the kernel's block index number, and then launch child kernels for the algorithm to run. As you can see in the picture, the outer loop is vectorized since the loop size is known beforehand, but then as the outer loop is running, the inner loop can be vectorized because A, any kernel can now launch child kernels, and B, the GPU can actually resolve the inner loop size before the child kernel's launch time. In this case, the parallelism is carried out in an efficient manner and no resources were wasted. Here are some other interesting example applications of dynamic parallelism. As you may know, quicksort is a recursive sorting algorithm. Two important implementation details to note about quicksort is that 1. Subpartitions made by quicksort aren't necessarily of the same size, and 2. Some branches of quicksort may go deeper than the others. With dynamic parallelism, there is no longer any need to go back to the CPU to check whether any further processing down a branch is required, or if any further subsets need to be created for the quicksort partition. The GPU can handle the entire task on its own without any CPU intervention. Another application of this is the dynamic grid management. With dynamic parallelism, the grid resolution can be determined dynamically at runtime in a data-dependent manner. You can start with the coarse grid and then zoom in on areas of interest while avoiding unnecessary calculations in areas with little or no change. Here are a couple advantages of dynamic parallelism. It allows you to perform irregular parallelisms quite nicely, where irregular parallelisms are problems that don't really have a nice, well-balanced behavior and are usually hard to divide into independent subtasks. It also allows for better task parallelisms. The GPU has become more autonomous, and this allows the CPU to queue or request more tasks on the GPU with little or no management overhead. Dynamic parallelism also provides you access to powerful recursive algorithms that were not possible in the previous architecture. Along with these advantages, dynamic parallelism also adds a bit of complexity to GPUs and GPU programming. One of the difficulties of dynamic parallelism comes from the fact that it implicitly relies on recursion. Recursion isn't something that you can easily add to all existing algorithms, so taking advantage of dynamic parallelism will require some new algorithms to be specifically designed around it. Other complexities also include the need for developers to manage potentially complex ordering and concurrencies, and also a requirement for a new grid management unit. Here is a picture of the Fermi workflow. As you may notice, since the Fermi architecture only allowed CPUs to launch kernels, the workflow is very unidirectional. It only flows from top to bottom. Here is another picture showing the Kepler workflow. And as you can see, there are two main sources of work generated, one from the CPU and one from the GPU. And the grid management unit basically acts as an aggregator and manager of those two different workflows. This brings us to the end of my presentation. Next up is Kai, who will be talking about the memory hierarchy in the Kepler architecture.
My name is Xiaokai Li. In the rest of the presentation, I will introduce the memory hierarchy of Kepler architecture. At first, I will make a brief comparison between CPU and the GPU. And then, I will focus on the memory hierarchy of Kepler architecture. At last, I will introduce some new features of Kepler. We are very familiar with the memory hierarchy of CPU. A CPU has registers on the top, and then 3 levels of caches, and then main memory at the bottom. As we move down from the top to the bottom, each level of memory is getting larger, slower, and less expensive. A GPU has a very similar memory hierarchy, but it has only 2 levels of caches. In this slide, we can see more details of a CPU and a GPU. The left graph is a CPU that has 4 cores and 3 levels of caches. L1 cache is built into the core, so each core has its own L1 cache and its own L2 cache. L3 cache is shared by all 4 cores. The right graph is a Kepler architecture which we have seen earlier. It has multiple blocks. Each block has multiple cores. In the middle of the graph, we can see there is L2 cache. L2 cache is shared by all the blocks. Each block also has its own L1 cache, which is the blue area inside each block. Now let's move to our main part, the memory hierarchy. In this part, I will introduce 5 types of memories. The first one is local memory. Local memory is the memory where registers and other thread data is built. It is called local because it can only be accessed by its own thread. In a core, registers are limited resources. When registers run out, some data will be moved to local memory. Local memory is not real physical memory, but an abstraction of global memory. So accessing local memory is as expensive as accessing global memory. Shared memory. It is the memory that resides in the block, so it is visible to all the threads within that block. It enables the communication and the data sharing among the threads within the block. Global memory. It is visible to all the threads in all the blocks. It can also be accessed by the host and the device. So it is responsible for the data transfer between CPU and the GPU. Constant memory. It is visible to all the threads, but it is read-only. We can store a constant variable in constant memory, such as pi equal to 3.14. When we run an application, we can read pi, but we cannot change pi. The advantage is it reduces the required memory bandwidth. Texture memory. It is visible to all the threads. It is also read-only. It is optimized for 2D read operations. When reads are physically adjacent, using texture memory is more efficient and can speed up the performance compared to global memory. In this slide, we can see how each type of memory corresponds to the software and hardware. Local memory can be accessed by its own thread, which is generated by a CUDA core. Shared memory can be accessed by all the threads in a thread block, which is generated by a block. Global, constant, and texture memory can be accessed by all the threads in all the blocks in a GPU. If we put all the memories together, we can see a graph like this. This is a simplified illustration of a GPU. So this is an overview of all the memories and the scope of each type of memory. In this table, I summarized all types of memories. We can see shared memory is built on the chip. Other memories are off the chip. Local, shared, and global memory have read and write access. Constant and texture memory have only read access. And we can also see the scope and the lifetime of each type of memory. In this slide, we can see some new features of Kepler architecture. It made a lot of improvements over Fermi, which is the previous generation of the GPU released by NVIDIA. The first one is the 64 KB configuration of shared memory and L1 cache. In Fermi, 2 configurations are allowed. The first one is 48 KB L1 cache plus 16 KB shared memory. The second one is 16 KB L1 cache plus 48 KB shared memory. In Kepler, the third configuration is allowed, which is 32 KB L1 cache plus 32 KB shared memory. This makes the configuration more flexible for the programmers. Kepler also introduced a 48 KB read-only data cache. Kepler also doubled L2 cache memory in Fermi, which makes it 1536 KB. Kepler also has the feature of memory protection support. So in this slide, we list all the references we used for our presentation. So please email us if you have any questions or any feedback. Thanks a lot for watching.